If you've ever spent time in a kitchen, you probably know the golden rule of a grease fire. Never, ever throw water on it. The moment that water hits to boiling grease, it instantly vaporizes, violently throwing flaming oil into the air. This reaction shows us the most important rule of fire safety. To fight a fire safely, you have to know exactly what material is burning first so you can choose the right tool for the job. Now imagine trying to apply that rule while flying 30,000 feet in the air. Up there, you can't just call the local fire department. You are completely isolated, and you have to rely entirely on what you brought with you. To solve this problem, engineers treat a commercial airplane a lot like a flying house. Instead of one big open space, the plane is divided into distinct rooms or zones. The passenger cabin is like your living room, the engines are like the garage, and the cargo hold is the basement. Each of these zones has entirely different fire risks, requiring different defense tools. Aircraft survival doesn't depend on one giant, all-purpose fire extinguisher. Instead, it relies on a network of localized, highly specialized systems working together automatically. So how exactly does an airplane feel a fire starting across all these different zones? In the passenger cabin, the air is relatively calm. Here, the plane uses optical smoke detectors, which work a lot like the ones on your ceiling at home. They continuously monitor the air, looking for physical smoke particles to cross a tiny beam of light. But if you put that same smoke detector inside a jet engine, it would fail. The air inside an engine whips by at hundreds of miles per hour. Any smoke is blown away before a sensor catches it. As you can see in this diagram, the engine uses a specialized solution called a continuous loop system. Instead of looking for smoke, engineers wrap a long, heat-sensitive wire all the way around the inside of the engine. It acts like a nerve ending. If any point along that wire gets too hot, the material reacts, allowing electricity to flow. The wire instantly feels that heat and shoots a warning signal straight to the cockpit to trigger an alarm. By combining optical sensors inside the cabin with these thermal nerves outside in the engines, the aircraft builds a complete detection network. No matter the physical environment, a fire cannot hide. Once the plane knows a fire is there, how does it actually put it out in the passenger cabin, our flying living room? The cabin faces two common threats. The first is a fire involving solid materials, like paper, cloth, or luggage. The second involves electronics, like the wiring inside seatback screens. Because the cabin is easily accessible, humans handle the response manually. Flight attendants use water extinguishers to cool and soak solid materials. But for electrical fires, water is dangerous. Instead, they use a specialized residue-free gas called halon, which smothers the flames without conducting electricity. The engines, our flying garage, are a completely different story. These are high-risk zones for liquid fires, fueled by aviation gas and lubricating oil. If you tried to use water here, you'd get that exact same violent explosion we saw in the kitchen grease fire. To fight an engine fire, the pilot relies on a single vital piece of equipment, the fire switch, located right on the overhead panel. This diagram outlines the automated logic that kicks in when that switch is pulled. Step 1, it immediately closes the valves, cutting off the flow of fuel to starve the flame. Step 2, it discharges a high-pressure bottle of extinguishing gas directly into the engine casing to smother whatever is left. This mechanical sequence of starvation and smothering isolates the danger in seconds, safely neutralizing a severe liquid fire mid-flight without exposing the crew to danger. That brings us to our final question. How does the plane protect the cargo hold, our flying basement, when humans cannot physically go down there during a flight? For these isolated areas, engineers designed a specialized automated response, known as the dump and meter system. Looking at this cross-section of the cargo hold, you can see the first phase. The moment the optical sensors detect smoke, a high-rate bottle instantly discharges, dumping a massive volume of suppression gas to quickly knock down the initial flames. But airplanes aren't completely airtight, and gas slowly leaks out over time. So the system enters the meter phase. A secondary set of bottles begins slowly trickling a continuous flow of new gas into the hold. This maintains the exact chemical concentration needed to keep the fire suppressed for up to 3 hours. Because no human can go down with a fire extinguisher to check the basement, this delayed action automation guarantees the fire stays controlled, buying the pilots the critical time they need to reach an airport safely. When you buckle your seatbelt, you are entering a machine designed to monitor its own health every second of a flight. This graphic brings together the threats we've looked at today: fires in solid materials, liquid fuel fires, and electrical fires. The true benefit of aircraft fire protection is that it matches the right chemical tools to each of those specific threats, localized by zone, so the pilot never has to guess what to do. I hope knowing about these invisible systems makes your next flight feel a little bit more comfortable. If you enjoyed learning how this works, please like this video, subscribe to the channel, and let us know in the comments which aircraft system you want us to explain next.